Okay, so let's take a look here at the electrochemical cell. So far we've been talking about redox reactions, and you know that in order for an oxidation reduction reaction to occur, electrons have to be transferred from one reactant to another, okay? And when we're using these spontaneous redox reactions to produce electricity, we are putting together something called an electrochemical cell. Okay, so electrochemical cells are portable sources of electricity that use a spontaneous redox reaction to produce electricity. So this is what batteries are. Okay, and electrochemical cells are also called a couple other things. They're also known as voltaic cells and galvanic cells. So all of those terms are synonymous with each other. Okay, and the basic design of a electrochemical cell is down here at the bottom of the page. So let's bring this image up here. Okay, so we have two compartments, and one of the compartments is where oxidation is occurring, and the other compartment is where reduction is occurring. And they call these compartments half cells. So we bring the half cells together, and each half cell is going to contain an electrode. So for instance, here in the oxidation half cell, I have a magnesium electrode. It's just a piece of magnesium, and it's in a solution here with its own ions. So we've got magnesium ions in the solution, okay? And this is called the anode, okay? So the anode is where we are losing electrons, okay? So the electrons travel along this external wire. And here they're traveling from magnesium through this external wire over to the other half cell where reduction takes place. And where reduction takes place, this is where we are gaining electrons. And the half cell over here contains a different electrode. It contains a piece of copper. That's the electrode. And it's in a solution with its own ions. We've got these copper 2 ions in the solution. And this is called the cathode, where you're gaining your electrons. Okay? We connect the two half cells with something called a salt bridge. So this right here is your salt bridge. And I'm going to talk more about it when we get to the next page. Okay? And we can produce electricity when we have a spontaneous redox reaction occurring in this electrochemical cell, and it'll give us a certain amount of voltage. And that voltage can be read with a voltmeter. That's typically connected with those external wires. Okay? Any questions for me so far? Nope. Okay. So you can predict which direction the electrons will flow by looking at this table. So look at the purple side of the laminated page that I gave you. This is also in the back of your book, okay? So look on the left side where it says table A7. And what you're looking for is the electrodes and the ions that are in the solution. So whichever one is further towards the bottom, that one will give up electrons to the one that's above it. So we're looking for magnesium and copper. Okay, so down at the bottom, do you see the magnesium? It says Mg plus 2 electrons produces Mg solid. Okay, and then up above that, you're looking for solid copper. and a copper 2 ion. So if you go a little bit further up from there, like maybe halfway down the table, do you see it?
Yes.
Okay. So since the magnesium is below the copper, the magnesium will give up its electrons to copper. So that's why you're seeing these electrons flow from the magnesium electrode over to the copper electrode. Does that make sense? Okay. Okay. Now, let's take a look at the next page. So let's go over here. So they gave us a few notes. So let's highlight these. Oxidation, which is loss of electrons, that happens at the anode, always. And then reduction, which is where you are gaining electrons, that happens at the cathode. Okay? And since you are losing electrons at the anode and gaining electrons at the cathode, one of those will end up losing mass, while the other electrode ends up gaining mass. So wherever you're losing your electrons, this is going to lose mass. So I'll make a note that the electrode loses mass, and then at the cathode, this electrode gains mass, and you'll actually see that mass start to accumulate on the electrode itself. Okay. When something is gaining mass, they will sometimes refer to this as plating. Okay. Any questions on that? Okay, let's take a look a little bit further down here. Let's talk about the salt bridge. Okay, so let's look at this image here. They give us a little bit more detail. Okay, so I'm going to highlight the salt bridge like we did on the previous page. So a salt bridge allows ions to move towards one half cell or the other, and it counters the direction in which the electrons are flowing. Because if we didn't do that, we would end up having an imbalance of charge, and then this reaction wouldn't be able to proceed. Okay, so basically the salt bridge allows this continuous flow of electrons to occur. And when you're looking at the salt bridge, you're going to notice that here we have the ammonium ion, which is a cation. Okay, so the cations are flowing towards the cathode. Okay. Because that's where the electrons are moving towards, so it sort of counters that negative charge, okay? And then we've got the nitrate ions here. Nitrate ions are anions, and you've got these anions migrating towards the anode. So anions flow toward the anode. And here we've got our magnesium electrode. And when the electrons leave, it's converting this solid magnesium electrode into magnesium ions. So these magnesium ions that are being produced, that positive charge is being countered by the negative charge from the anions that are moving towards it, okay? Okay, so here, anions migrate toward the anode, and cations migrate towards the cathode. Okay. All right, turn the page. Let's take a look at the quick check. So with the person sitting next to you, why don't you answer these 4 questions, and then let's see what you guys come up with. That doesn't really appear, does it? At all. That's kind of funny. Okay. All right. So when you guys looked at the table, you're looking for silver and a silver ion, and then the chromium with the Cr+3. So when I look at the table, I see the chromium down at the bottom, and then I see the silver way further up towards the top. So that means that the electrons are being moved from chromium over to silver. Agreed? Okay, so the electrons are traveling along this external wire from the chromium electrode over to the silver electrode, like that. Okay, so that means the electrons flow to the left. You could say that they're going from the chromium electrode to the silver electrode. Are we cool with that? Okay. All right. And then which electrode is the anode?
The chromium.
So what does it say back on the previous page about the anode and the cathode in terms of electrons?
Reduction occurs.
So oxidation happens at the anode, right? So this is where oxidation happens. So this is where we're losing electrons.
And the chromium is losing the electrons.
So the chromium solid is the electrode. So this right here is the chromium electrode. Okay, this over here is the silver electrode. All right, any questions on that? Okay, and then in which direction do the cations flow through the salt bridge? Okay, so what does it say on the previous page?
Cations flow to the cathode.
So they flow to
Cathode.
the cathode. Okay, so this was our anode. and this one is our cathode. Oops. Okay. So that means it would go to the silver compartment. Okay? Or in this case, they're flowing to the left. Okay? And then which electrode gains in mass?
The silver electrode.
Yeah. Okay. So you would actually see the silver like plating on this electrode. Okay? Any questions about that? Yeah.
How do you figure out again how what direction the electron
It's going. So when you look at this table, okay, which is also in the back of your book, okay, you're looking for the half reaction that's on the bottom. So for instance, we've got chromium towards the bottom. Do you see where it says Cr plus 3 electrons is going to Cr solid? And then go way above that, like a quarter of the way down the table, you'll see Ag plus 1 plus an electron going to silver solid. Since the chromium is down at the bottom, it will give electrons to the one that's on the top. That's the direction of electron flow, okay, for these spontaneous reactions, okay? Okay, let's take a look at the next page. So what I'm going to teach you how to do here is I'm just going to jump straight into a practice problem, and I'm going to teach you how to use the table with the half reactions to predict how much voltage that spontaneous redox reaction will actually produce, okay? So there's a couple of different ways that they convey, let's erase this, that they convey the compartments to you. So in number 1, here's one of the compartments. So you have a nickel electrode with nickel plus 2 ions in the solution. And then the other electrode is Br2, and that will be in bromide ions. Does that make sense? And then when you look at number 2 is telling you, here is one of the compartments, and they separate it with this, these like parallel lines here. And then here's the other compartment. Okay? So we're going to refer to the table to figure this out. So let's look at the table. You're looking for nickel and bromine. And I found on the table, I found Ni plus 2 electrons. And then I've got nickel solid. Okay. And then I've got my bromine like a quarter of the way down the table. Actually, I should put these in the proper order. So let me put the bromine up above it. So bromine is here. Like this. And this voltage is a positive 1.09. And then the nickel as it is written, and I'm just doing this to explain something. I can't find the nickel.
I found it.
What is it for the voltage?
Negative 0.26.
Thank you so much. Okay, so that's how they're written in the table. Which direction will electrons flow?
Up to the bromine.
Yeah, so the electrons are going to go from here to here. We agree on that? Because of their location in the table. Now, what you have to do to figure out the overall reaction and the voltage is you take the half reaction that's on the bottom, and you are going to reverse the order, which means you're going to change the sign on the voltage. Okay, so this is going to be Ni solid going to Ni plus 2 electrons. And then if this is a negative 0.26, this becomes a positive 0.26 volts. Does that make sense? You only reverse the one that's giving up the electrons because you need to put these electrons on the product side. Does that make sense? Okay. You leave the other half reaction alone. Okay. So here are the two half reactions. One of them is losing electrons, the other one is gaining electrons. Okay? Now what we do is we add them together. And if you have the same number of electrons on the reactant and the product side, they cancel. So these and these cancel. Why are they still outside?
What is that?
Seniors. So we have bromine combining with solid nickel, and we're getting, and the order that you write these reactants and products doesn't matter. There's your overall reaction that's happening, okay? And then you add together the voltages. What is this? 1.34? Is that right? 1.35. Thank you. Okay. So that's how much voltage you would get. Does that make sense? Okay. So what I want you to do is do what I just did in number 2. And let's see what you come up with.
Still voluntary.
Mm-hmm.
Since it's Cu plus 2, I think it would actually be 0.34.
So there's 2 Cu plus 2s on here. Yeah, there's one that's going to Cu plus 1. And then there's a Cu plus 1 going to Cu solid. And then there's the Cu. Oh, yeah, you're right. That's 0.34.
Yes.
This one. Okay, did you come up with this for giving up the electrons? So then you reverse the order of the aluminum half reaction. Okay, now once you get to these two, let me switch colors here. You need to make sure that your electrons match, because if you've got 2 electrons here and 3 electrons here, what's the lowest common multiple of 2 and 3?
6.
6. So you would want to multiply this reaction by 3. Don't multiply the voltage. And then you'll multiply this half reaction by 2 so that the electrons match, so that they cancel. Okay? Once you do that, you're going to end up with this as your overall reaction. And then what is this? 0, 1, 0. What is this? 2 volts, I believe?
Yeah.
Okay.
No. It's
So we would spontaneously make 2
Yes.
volts.
yes.
Okay. Any questions on that? Okay, I just have a couple more things to mention and then we're all done learning new material for the whole year. Okay. All right. I'll wait for you to finish writing this. Okay. Let's look at corrosion over here for a second. Have you guys ever seen something rust? Okay. So rusting is the corrosion of iron. And it is not a desirable oxidation reaction. Okay, it's an unwanted oxidation. And it costs a lot of money to repair the damage that rust causes to buildings and ships and cars. Okay? So I need you to understand that rusting is an example, or corrosion is an undesirable redox reaction. Does that make sense? Okay. Now, turn to 13.3 right here. This is all I'm going to mention. Okay. So when you're using a non-spontaneous redox reaction, so in the section that we just covered, we were using spontaneous redox reactions to generate electricity, right? Okay, here we're going to use non-spontaneous redox reactions. And we have to use something to drive it. So typically you use electricity to drive a non-spontaneous redox reaction in an electrolytic cell. So I'm going to make this note that this uses a non-spontaneous redox reaction. And in order to get that reaction to go, I've got to plug it in. Okay? We're done. That's it.